Hello? We are rambling. Paper 1, November 2022, from the department. Let's do it. Given f of x is equal to x squared, determine the minimum distance between the point 10, 2 and a point on f. Okay, so we have got f of x is equal to x squared is just this parabola. Well, not this one exactly, but you know, very basic parabola, turning point on the origin, hasn't moved left or right, up or down, etc. And then we've got the point, I don't know, oh, okay, let's say somewhere here, the point 10 and 2, right? And we want to find the shortest distance between 10 and 2 and some point on f, right? So for example, we could take the point that would be on the same horizontal line as this guy, so that would have a y coordinate of 2, and it would be positive square root of 2 as the x, right? Because if I square that, I get 2, right? So the distance here would just be 10 minus the square root of 2, which I'm going to imagine, well, square root of 2 is 1 comma some, so it's going to be 8 comma something, right? Or we could look at the distance between this point 10, 2 and the origin, right? You know that that's another point on f, and that distance, we could use the distance formula, right, to figure out. So that distance would be the square root of 10 minus 0 squared plus 2 minus 0 squared, which would be 100 plus 4, so 104, and that's going to be 10 comma something. Okay, so that distance is longer than this distance, right? So we are trying to find which point will be the closest to 10, 2, right? And if we talk about shortest, longest, minimum, maximumist, my thoughts immediately incline to optimization, right? So I want to find a general expression for the distance between this point and any point on the parabola, right? So the first thing that we can figure out is that if the x-coordinate of some point on f is x, then the y-coordinate will be x squared, right? And therefore, the expression for the distance between these two will be given by the square root of x minus 10 squared plus x squared minus 2 squared, right? And of course, we know that we can switch these around, doesn't really matter because of the squaring that's happening. Yawn. Right, so this is what we are trying to optimize, right? Oh, my goodness. So, I mean, okay, so there's tricky things happening here. So, if we call this function the distance given some value x, then it looks like this. Okay, now the question becomes, how on earth do we differentiate that? Now, once you have done a bit of advanced calculus, say like your first year university maths, you would use something called the chain rule, perhaps, to differentiate that. We, however, are not so advanced, so we need to think of a workaround, I think. So my thinking is that this is always going to be a positive number, right? Because a square is at least 0, likewise here. So at the very least, this value here will be 0. And I mean, it won't be 0 because this point doesn't lie on anywhere on f. So the distance between it and some point on f will always be greater than 0. Anyway, so the point is this is going to be some positive number, right? So if I want to find the number that, the smallest that this can be, then it's just the same as me finding the smallest that this can be, right? So can determine minimum D by figuring out minimum x minus 10 squared plus x squared minus 2. Right, so we are trying to figure out, oh, it is confusing that I've used D because we used that for derivatives as well. So I'm just going to call it capital F. Okay, so now I want to use, so the first derivative of x minus 10 squared plus x squared minus 2 squared. I'm going to first need to simplify my expression as much as possible. So this will be x squared minus 10x minus 10x, so that's minus 20x, and then plus 100. And then here I've got x squared minus 2 times x squared minus 2, so that's going to be x to the 4 minus 2x squared minus 2x squared, so that's minus 4x squared plus 4. Okay, right, then we are still simplifying. We'll get to the differentiating just now. So let's look at our like terms. We have an x to the 4 that's just chilling by itself. Then next up we have some x squared terms. So this is one of them. This is another one. So they add up to minus 3x squared. And then we have some x terms. So minus 20x. Yep, that's it. So that'll be minus 20x. And then we have our constants, which add up to 104. Okay, so now we're trying to find the first derivative for this expression, which will be 4x cubed minus 6x minus 20. Okay, so if we look at this graphically, this is, well, okay, no, why am I looking at the graph? I don't care about the graph. Okay, so in order to find, well, okay, I guess, yeah, that's why I would look at the graph. In order to find where this is maximized or minimized, I don't know what a graph, I think these are called QUARTIC expressions. I don't know what the graph of that looks like. But this is the first derivative. It's a cubic expression. So that tells me that, okay, we know that it's probably going to be equal to 0 in 2 places, 3 places. It could be equal to 0 in 3 places. So this is possibly then a function where that has got 3 turning points. Yo, this is giving me heebie-jeebies. This is giving me severe heebie-jeebies. Anyway, let's just commit to it. So we are interested in where 4x cubed minus 6x minus 20 is equal to 0, right? Because we're trying to find the turning points of this guy. Oh, okay, don't have to go all the way up there. But yeah, the turning points of this guy, this function. We can divide through by 2. And then this is interesting. I don't know how to factorize it. Let's just start with guesses. So let's see, when x is equal to 1, what happens? So this is 2 times 1 minus 3 times 1 minus 10, which is 2 minus 3 minus 10, which is minus 11. And in fact, okay, let me just try with x is equal to 2. So we have 2 times 2 to the 3 minus 3. Oh, this looks promising. So this is 16 minus 6 minus 10, so that is 0. Okay, so this is x minus 2 is one of the factors. And then we know that, okay, firstly, let's just get you guys out of the way a little bit. Okay, right, so we know that this is going to be 2x squared, and the last bit is going to be a plus 5, right? So the x times this gives me that, the minus 2 times that gives me that. And then this part over here, which I'll just call bx for now, when I times it with this, I'm going to get an x squared term. We currently don't have one, i.e. we have a 0x squared term, so it will contribute to that. And when I times it with this, I will get a bit of this term. When I times this with this, I will also get a bit of the 0x squared term. And when I times, what am I still missing? Right, so this one gives me this. This one gives me a bit of the x squared term. Oh, and then this one gives me a bit of this term, the x term. This one gives me a bit of the missing x squared term. This one gives me part of the x term, and then this one gives me the constant. Okay, so what we want is so I'll start with x times bx squared, and then x times 5, which is 5x, and then minus 2 times 2x squared. In fact, I'll just stack this down here. Okay, and then finally minus 2 times bx. That needs to add up to a 0x squared, because you don't have an x squared term, and a minus 3x. Okay, so I can then see that my b is meant to be a 4, right? Oh golly. So it is meant to be a 4, so that I have 4x squared minus 4x squared is 0x squared, and we can double check here. So 5x minus 2 times 4x, so this is minus 8x, does in fact give me minus 3x. So this does work here as well. Yo, this eraser is maybe just a little bit too violent. Okay, so that is that. Okay, so my b is a positive 4. Okie dokie. Alright, also going to squish that into a corner somewhere. Okay, now can I factorize this? So I'm looking for factors of 2 times 10, 2 times 5, which is 10. That will add up to 4. So we have 1 and 10, and 2 and 5. None of those work. So we can solve this using the quadratic formula. Let me first see if there are even solutions. So delta of the discriminant will be 4 squared minus 4 times 2 times 5. Yeah, that's already looking fishy. So 16 minus 8 times 5 is 40. So that is minus 24, which is smaller than 0. So therefore, the only solution, the only real solution here is when x is equal to 2. So that means that this guy only has one turning point, and that turning point occurs when x is equal to 2. Okay, so x to the 4 squared minus 20x plus 104, one turning point when x is equal to 2. Okay, so let's look at the second derivative so that we can determine whether, or just confirm whether it is a minimum or a maximum that occurs here. So I don't actually know how to write second derivative with this notation, so I'm just gonna go right ahead and write it the way I know how. I doubt myself. Is this how we write it? I think this is how we write it. Anyway, don't quote me. So the second derivative of this expression that we started out with will be, okay, the first derivative of this guy, right? This guy. So I'm just going to chop that and bring it over here. So that'll be 12x squared minus 6. Okay, so now we're interested to see what is the concavity of the graph when, well, okay, I'm actually just curious about the concavity of the graph in general. So I'm just going to 12x squared minus 6. Okay, so I want to know, where is it equal to 0? Where is it greater than 0? Where is it smaller than 0? Because that will then tell me about the concavity of this function, right? So 12x squared minus 6. So let's first figure out where is it equal to 0. Divide through by 6. So that is 2x squared is equal to 1. So x squared is equal to plus or minus the square root of a half, which we can also write as plus or minus the square root of 1 over the square root of 2. If we rationalize the denominator, then we end up with the square root of 2 at the top and a 2 at the bottom. Okay, so skipped a couple of steps there, sorry. So am I able to move this? I highly doubt it, but I'm going to try anyway. So the step that I missed here is x squared is equal to 1 over 2, and then we take the square root on both sides to just get x. Okay, so sorry, this is plus or minus that. Okay, so we know that 12x squared minus 6 is a parabola that looks like this. So it's equal to 0. This would be positive root 2 over 2, and this would be negative root 2 over 2, right? So between those two x values, it is negative, and on these extreme sides it's positive. So what is this telling us? So this is telling us that the function x to the 4, and I really should just name this function, this is not really looking too good, but anyway, let's just pretend it is a function. This guy points of inflection occur at x is equal to plus or minus root 2 over 2, right? And then we know that when x is smaller than negative root 2 over 2, or x is greater than root 2 over 2, the graph is concave up, because for those x values, the second derivative is yielding positive values, okay? And then we know that when x is between negative root 2 over 2 and root 2 over 2, the graph is concave down. Okay. Right, and we know that there is a turning point when x is equal to 2. So if I were to just take a stab-a-roo-roo at this, hey, what does this mean? Okay, so if we have, right, and we have minus root 2 over 2 and positive root 2 over 2, and we know that we are concave up over here and over here, and over here we are concave down, okay, and we have a turning point somewhere over here, right, when x is equal to 2. This is so interesting. Okay, so this is what? Concave up, but no turning point, and then concave down, and then concave up. Potentially that's what it looks like. So I would really just like to get an x-intercept, or maybe let me figure out a y-intercept. Maybe that will help me. That's going to be easier to work out. Let's see. Y-intercept for y is equal to, I can't keep writing out this function. Let's see. Okay, I'm really like properly derailed here, but I hope you are as curious as I am about what on earth this graph looks like. So we will figure that out by saying y is equal to 0 to the 4 minus 3 times 0 squared minus 20 times 0 plus 104. So that'll be positive 104. Okay. Let's also get the y coordinate of the turning point, the single turning point that we have, y coordinate of TP. So that we will get by subbing in x is equal to 2, where the turning point occurs. So 2 and 2 and 2. Okay, so that is 16 minus 12 minus 40 plus 104. Okay, so that's something very positive. So that is 68, I think. I think so. So yeah, okay, so this sketches off. So it is going to be concave up, but there's no turning point, so just, okay, I'm gonna need more space. Okay, so let's, oopsie, move this guy down here and expand him. Okay, that didn't work out so well. But anyway, never throw a diagram away. So that means, okay, so we said it's concave up, but no turning point, but it does change concavity here, and then it changes back. Yo, guys, okay, also, okay, maybe it is time to throw a diagram away. Okay, so just imagine some beautiful elevator music at this point. And let's do this. Wow. Okay, a lot of the action is happening above the x-axis, so I'm going to give a lot of space to that. Okay, then we know that minus root 2 over 2, a point of inflection occurs. Positive root 2 over 2, another point of inflection occurs. And then somewhere else, there we have a turning point. And we know that is concave up over here and over here, and it is concave down over here. And in fact, we don't even need the sketch to know what kind of a turning point will occur here. Just by virtue of knowing that it's concave up here, we know that there is a minimum that is occurring here, right? So really, that's all we need. However, curiosity has gripped, so concave up and then concave down. Okay, and then it switches slowly to concave up again, and then we have a turning point. Okay, I'm going to take one more shot at this. Concave down, okay, and then a slow switch to concave up, and our turning point is over there, right? And point of inflection over there, point of inflection over there. Okay, so really all we care about is the fact that this is a minimum turning point. So this expression has its smallest value when x is equal to 2, right? And so to go back to the original question, right, determine the minimum distance between the point 10, 2 and point on F. We know that the minimum distance occurs when x is equal to 2, right? So that would be maybe somewhere here. And when x is equal to 2, the y coordinate is equal to 4. The distance between these two will be 2 minus 10 squared plus 4 minus 2 squared, which will be equal to 8 squared 64 plus 4, which is the square root of 68, for which I will request assistance from the calculator that is currently sleeping. Okay, square root of 68 is about 8,2, let's say 8,25 units. 8,25 units. Okay, so let's just go through that wild journey again. Okay, right. So minimum immediately just made me think of optimizing. So first thing we want to do in an optimization problem is to figure out some function that describes the value that we are trying to optimize, right? So in this case, we're trying to optimize the distance between this point and a point on this parabola. So I then use the fact that, okay, for any point on this parabola, if its coordinate is x, the y coordinate will be x squared. So then the distance between this point and this, well, any point, will be given by x minus 10 squared plus x squared minus 2 squared, right? The square root of that will give us that distance. So we would then at this point want to find the first derivative of this expression so that we can figure out where its turning points are and therefore establish that, oh, okay, at such and such an x value, this is where the minimum value of this expression occurs. However, the problem is remember that in order for us to apply our shortcut rule for differentiating, we need to get our expression to look like ax to the power of n plus bx to the power of n minus 1 plus right? And right now, the biggest thing that is standing in the way of us doing that is this big square root that is umbrellaing the whole expression. And because there are two terms down here, we can't even apply like one of our nifty exponent rules, because those ones work if what's down here is a product or a quotient. So from there, I decided that, you know what, the easiest thing is going to be if I find the value of x that makes this expression as small as possible, because if this is as small as possible, then the square root will also be as small as possible. And a couple of things aid this. So firstly, we know that this can't be negative, right? Because if there was a possibility that it could be negative, then this being as small as possible wouldn't necessarily give us the smallest value for this, because the square root of a negative is non-real. So that, if there was a possibility that this could be negative, that would be awkward, right? The second thing, that's probably the only thing. So anyway, having satisfied myself with the logic that, okay, if I can find the x that makes this as small as possible, then I found the x that makes this as small as possible. That is what I proceeded with. So in order to find the x that minimizes this, I needed to find the first derivative, right? So in order to do that, needed to multiply out and simplify this expression, which gave us this. And I am happy with how that turned out. And if we simplify it, we have x to the 4 minus 3x squared minus 20x plus 104. And the first derivative of that is, I'm happy with that. Okay, so now the next thing is we needed to find where the turning points occur for the function y is equal to this, right? And we do that by equating the first derivative to 0. So I did that. Divided through by 2 and got that. And now the next mission was to factorize this so that I could find the solutions. Tried out x is equal to 1 to see what the value of the expression will be when x is 1. That didn't give me 0, so it's not one of the solutions. But when I subbed in 2, I did get 0, so that tells me that x is equal to 2 is one of the solutions to this equation, which means if I factorize it, one of the brackets must be x minus 2. We then did our magic to figure out what the second bracket would be. And before going through the heartache of putting this into the quadratic formula, I just thought, you know what, let me check if it even does have any real roots. And it turned out that nope, the discriminant is smaller than 0, so it won't have real roots. So the only solution, so I should actually probably have explained that here. Therefore, other bracket does not yield real solutions. Okay, right. So then, we established that there is in fact only one turning point, and it occurs when x is equal to 2, right? So then we just need to confirm that the turning point that occurs here is in fact a minimum turning point. I mean, the question suggests that it is, but always good to make sure. At this point, what would be sufficient would be to find the second derivative of this expression, sub in the x is equal to 2. If you then get a number that's smaller than 0, then you know that at that point the graph is concave down, and so you have a local maximum. But if you sub it in and you get a number greater than 0, then you know that at that point the graph is concave up, and that turning point is a local minimum. So that's what we could have skipped right ahead to, but curiosity got the better of me. I was then just curious to see what this graph looks like. So found the second derivative of this expression, which we did by finding the first derivative of the first derivative, right, which is this guy. So that gave us 12x squared minus 6. Okay. And so, yeah, what I was curious about here was the concavity dynamics. So where is the second derivative equal to 0? Where is it negative and where is it positive? And because of the shape of the graph that represents this expression, which would be a positive-ish, yeah, we don't say positive parabola, but a smiley parabola, right? And it's moved down 6 units, hasn't moved left or right, so it would look something like this, right? And we were able to find what the x-intercepts would be, so we could then see that, okay, when x is smaller than this number and when x is larger than this number, then this expression yields positive values. But when x is between these two numbers, then the expression yields negative numbers. And what does that tell us about this guy? So it tells us that when x is equal to these numbers, we have a point of inflection, right? So the concavity is changing. When x is smaller than this or bigger than this, then the graph is concave up because the second derivative is positive. And when x is between these two numbers, then the graph is concave down. Okay. Right, so that's what that whole spiel was about. I was still then confused about how exactly to draw this thing, so I just figured out other points that might help me. The y-intercept is an easy one to work out, and we got that, okay, the y-intercept occurs at 0, 104. And then I also just wanted to figure out what is the y-coordinate of the turning point. Is it occurring above the x-axis, below the x-axis? I should have known that it would be above the x-axis because this expression represents distances. So we fully expect that all the values that it yields will be 0 and above, right? So anyway, so we found that the y-coordinate occurs at 68. So this is what the graph ends up looking like. So we have a concave up situation up until here, right, up until this point of inflection. Then the graph becomes concave down. Oh, golly molly. Right, concave down, mine is very subtle, okay. And then it starts to change again to concave up. And this is where that minimum occurs, and otherwise it's to infinity and beyond. Anyway, after all of that adventuring, we return to the point. I mean, I didn't even need to work this out again because we saw that when x is equal to 2, then this expression, the expression underneath the square root, yields 68, which is what we get here anyway. So the distance will be the square root of that, which is 8.25 units, and that is the smallest, the shortest distance that can occur between the point 10, 2 and any point on the parabola y is equal to x squared. So let's see what the memo has to say about our rambles. Yeah, the agreement is that the shortest distance is 8.25. Okay, cool. So let's see if there's anything they did differently. No. Yeah. They don't even confirm what kind of a turning point it is, but yeah. Anyway, so that was definitely a ramble in the true nature of this channel, but I do hope it was a useful ramble as usual. Catch you another time for another chat. I was busy recording another video wherein I caught a glimpse of a question 9.2 in the memo, and I freaked out thinking, oh my goodness, did I record an incomplete video for question 9? Anyway, it turns out that the 9.2, air quotes, is just another an alternative way of approaching this question that actually looks so cool. So the approach that they take, the second approach that they take in the memo is they say, okay, cool. So we have this parabola, y is equal to x squared. And then we have this point, 10, 2, right? So if you join this point with a point on the parabola, right? And you were to imagine how do I want to say this? So you were to imagine the tangent at that point, okay? Oh man, okay, I need to think about this more clearly. I can see it in my head, but I suddenly have questions. So it kind of makes sense to me that the angle that this line will make to the tangent at that point will kind of undergo like a whole lot of value changes depending on where the point is. So like I'm just thinking now, if we put a point here, right, and we join the 10 to point to it, right, you can kind of see that it's, you know, this angle is different to this angle, okay? And for as long as this angle is not a 90, then this distance is not optimized because it's almost like a hypotenuse in a right angle triangle. Like if you were to join this point to something that is a 90-degree drop to the parabola, that will be a shorter distance than this. This is a shorter distance than that. So this distance is optimized when this meets the parabola at 90 degrees. So we want to find the point on the parabola where the distance, the line connecting this point to the mystery point is perpendicular to the tangent at the mystery point. So what they then do in the memo is they say, okay, cool, mystery point has coordinates that look like this. We don't know what the x is, but we know that that's what the relationship between the x and y coordinate will be. So the gradient of this line will be 2 minus x squared divided by 10 minus x. We'll switch them around, right? And the gradient of the tangent at that point will be the inverse of this, right? So, the negated inverse of it, nochal. So the gradient of the tangent will be negative 10 minus x over 2 minus x squared, and we can decide who this negative goes to, the top, the bottom. Wherever it goes, it's just going to cause a switcheroo, right? So that will be x minus 10 over 2 minus x squared. Or you could have 10 minus x over x squared minus 2, right? At the same time, we also know that the gradient of any tangent to this parabola is going to be given by the first derivative of x squared, which is 2x, right? So we are looking for a line, right, a line that joins 10, 2 and some point on the parabola such that it meets two conditions. Firstly, that line must be perpendicular to the tangent at that point, right? So we've said, okay, in general, the gradient of the line connecting this point with any point on the parabola is given by this guy. Now, we are looking for a point such that the gradient of the tangent is the negated reciprocal of that, i.e. the tangent is perpendicular to this line, and it's equal to, it must fit the expression that describes the gradient of any tangent to the parabola, which is this guy. So then they solve this. So x minus 10 is equal to 2 minus x squared is equal to, we can write this as 2x over 1, and then cross multiply. So then we have 2x times 2 is 4x, and then 2x times x squared is 2x cubed, and then on this side we have x minus 10, and then we've got minus 2x cubed minus 2, sorry, and then plus 4x minus x plus 10 is equal to 0, and that is minus 2x cubed plus 3x plus 10 is equal to 0. This looks very familiar, right? So if I just divide through by negative 1, isn't this in fact the equation we ended up solving? Yep, it looks like that guy. Funny. Okay, right, and we found that, of course, the solution, the only real solution that got yielded there was when x is equal to 2. So that told us that, okay, when x is equal to 2, this line is perpendicular to the tangent at that point, and so the distance between it and the point is as optimal as it can be. So yeah, that was an interesting take on the problem. Thank you for sticking around. Let's chat again another time. Okay, I won't lie, I am curious about what happens when you pick a point that's like over here. So then you have this line going like that. Yeah, I guess it's the same thing. So if you look at the angle between the tangent and this line, it's not really giving 90. But is there no point, like here maybe, where, I don't know, will it never be 90 as long as x is negative? I guess not. That's so interesting. That is so interesting. Anyway, things to play around with. If you're into GeoGebra, this is totally something that I would play with on GeoGebra, just to see visually, like, wow, the optimum distance only occurs when x is equal to 2, nowhere else. Anyway, I'm really saying goodbye now. Oops.